You're welcome. Just need to find the share again. Where is the share? Ah, yeah. Okay, two of this. Okay, so I'm saying that we are going to see how to combine high-throughput initial calculation with the power of machine learning that was introduced already by Matthias and Luca this morning. And so what we aim to do is, in material science, this is an important set of relations. So the processing condition of that you apply to a given synthesis basically has an effect on the structure that you manage to realize. And this structure in turn has an effect on the properties that you're going to get from the material and as a result of the performance of that. Okay. And so one of the ideas of machine learning is to be able to find these science relationships of cause and effect. So processing as a result of impacts the structures impact the properties, and the properties impact the performance. And thanks to materials informatics, if you have enough data about each of these relationships, you can try to infer some kind of forward model that predicts the result, the structure, as a result of the processing condition, the properties as a result of the structure, and so on and so forth. And it can be actually the performance as a result of the processing, the structures, and the properties. Okay, so this is one way to go. But ideally, what people would like to do is what is called inverse design. That is, what should I use as a process to obtain a given structure and given properties such that my performance is this? Okay, so we'd like to have this inverse models that are able to tell you what you need to do to get a given property. Okay, so in this talk, I will be focusing mainly on the central part of this picture. So the relationship between structure and properties. Okay, I'm not going to be speaking about processing because it's even more difficult, at least from an initial point of view. And the performance is very technical, so I'm not going there. Okay, so what we want is from a structure to be able to predict a property. Okay, we have a tool that we all know and that we use is ab initio calculations. Okay, so from a given structure, if you use one of the DFT codes, you're able to compute a number of the properties of the material. Okay, and now what we would like to do, because some of those that I already showed you are very time demanding, and so we'd like to have something that is faster for that. Maybe it's a bit less accurate. And for that, we would love to use machine learning. And for that, we will need, that's the next step, I will come to afterwards. Yeah, and to go to the other direction, the inverse design that I was mentioning before, this is going to be only done by machine learning. Okay, so we have machine learning in two places, for the inverse design and for the prediction to make it faster. Okay, and in both cases, machine learning requires databases because you need to learn that. And so to get those databases, there are two sources. One is the ab initio calculation, and so I discussed this morning, and the other one is the possible experiment. Okay, and possibly at one stage we'd like to combine both calculations and experiment to get better predictions. Okay, that's the whole point. We want to get better predictions, both on one direction to predict the property from the structure, or the other way around to be able to say, if I want this property, then I need this kind of structure. Okay, so that's everything we want to do. To do that, so to go in one or the other direction, there are actually three ways. So this is taken from a paper from 2020. So the first one is the one of the high throughput screening, where basically you take different materials. So I showed you the way it was working this morning. You do the high throughput, you do the ab initio calculation, and you only retain the materials that have the good properties. Okay. The second one is the global optimization. So there, basically, you have already a machine learning method that tells you for this structure, I get this property. Okay, and so you move in the space of the structures to minimize the property, to optimize the property. Okay, and finally, to go in the direction of the inverse design, there is what is called the generative models. And so I will spend a lot of time actually on the high-throughput, and then I'll say a few words about the other. Okay, so let me start with the high-throughput screening. So I already showed you this picture where basically, again, the idea is that you do as much as possible many calculations to screen different materials and to see which one meet the requirements that you have in mind to get a material that satisfies what you want in terms of properties. So that's not just one property, that's many properties. Okay. And of course, one of the points here, and of course you can synthesize it. One of the points here is Day2 and data mining, which I mentioned already. And I'm going to give you two examples of this, of what can be done with that. And then we'll see the limitations. Okay. So one example is to try to, can I move this thing here? More, maybe. Height. Okay, perfect. Okay. Okay, so one first example is about transparent conducting materials, which I already pointed to this morning. So the idea is that you want to have a material that is transparent and at the same time conducting. So these materials are very useful, for instance, in the case of touch screens. Sorry. So where basically you see that you have the upper layer of your panel that needs to be transparent because you want to see what's displayed by the screen, and at the same time when you touch it, the material has to react and some current has to go. So it's transparent and conducting at the same time. In the same way, in solar cells, when you have some light that shines into the material, so for it to shine in the material needs to be transparent, and then these photons, they come in the material and they create electron hole pairs that then need to be separated, one going to the upper gate and the other one on the backhand side. Okay, and so the transparent layer that lets the photon go through also need to be able to collect the carriers, so it needs to be conducting. So having such materials that are both transparent and conducting is a bit contradictory, because to get a good material that is transparent, you need a high band gap. And for it to be conducting, you need a small band gap. Okay, so this is really not straightforward. And so I'm going to show you how this can be achieved. So typically, one of the workflows that I was showing, so the funnel that I was showing in this case would be as follows. You want the material to be stable, because otherwise it doesn't last too much when you put it on the roof of your house, or when you have your cell phone. If all of a sudden it becomes not transparent, it's a bit annoying, or not conducting, it's a bit annoying. Then we want it to be transparent, and as I said, to get it transparent, you need to have a wide band gap in the material. We want it to be conducting. So for it to be conducting, if you look at the formula for conductivity, you have that sigma is equal to NQ nu, and nu is the effective mass. So you want a low effective mass. Sorry, the nu is the mobility, and the mobility is related to the effective mass, as mu is epsilon tau divided by m star, where m star is the effective mass, and so you want a low effective mass to have a high mobility and hence a high conductivity. Okay. So how do we get a low effective mass? A low effective mass means that you have a band that is very dispersive. Okay, a band that is very dispersive. You will have a second derivative that is big, and so if the second derivative is big, you have 1 over m star, that is m star is small, 1 over m star is big. Okay. If you look at typical oxides, which are usually the materials that I use as the transparent layer. So for instance, in your cell phone, it's called indium tin oxide that you have on on the screen of the cell phone. So the materials, these oxides, have typically the following band structure, where you have a band in the conduction part that is very dispersive, so with low effective mass. And in contrast, at the top of the valence band, you have a band that is not very dispersive, it's very flat, and so you have a high effective mass, and so that's not very good. And so in practice, what happens is that you dope the material in such a way that you have either electrons as conductors or holes as conductors, and you see that in that case you have a different mobility. In one case it's the mobility of the electrons, in the other case it's the mobility of the holes. And as I showed you in the previous slide, the mobility of the electron because of the band structure, okay, but because of the band structure that I was showing before, it's much better for the electrons than for the holes. So the mobility of the n types is basically 1 order of magnitude larger than the one of the p types. Okay, so as I was mentioning, in your cell phone, the layer that you have at the top is indium tin oxide, which is an N-type material. Okay, and so it would be nice to have P-type materials, because in that case, you would be able to do what is called a CMOS transistor. C stands for complementary. And complementary, that's because you have both N-type MOS and a P-type MOS. So you really need to have both type of conductors. Okay. So the question is, do we find such materials that have low effective mass? Is it searching a needle in a haystack, or is there a way to do some calculation and to find some materials in a decent amount of time? Okay. And actually, the answer is yes. So what we did is that we did this funnel thing with many compounds. We were using binary, ternary, and quaternary oxides. We screened 7,000 binaries, 7,000 compounds. And out of those, we identified this double peroxide, Day2, DI-TO6, which is rhombohedral, and it has a low effective mass. Typically, you see you have 0.4, 0.5. It has a high valence band maximum that favors the p-type, and we have computed the band gap in GW to be 3.8 cV, so that's transparent. So we have this material, and we were able to convince some experimental colleagues to synthesize this material, okay, which they did. They doped it with potassium, okay? And then when you look at the transparency, you see here you have something that holds the material, and you can see that the material, you see what's behind the material, so it's transparent, okay? And in terms of the conductivity, you see that this is the typical P-type conductors that I was mentioning, which have a mobility of the order of 10. So these are based on copper often. And the one that we propose is basically 3 to 4 times more mobile than those ones. Okay. So you see that we can use that. So we did a similar approach to many different materials. We found electrodes, we find high refractive index and wide bandgap materials, high Curie temperature for magnetic semiconductors, for spectronics, thermoelectrics, multiferroids. And I would just like to show you another one, which is for, it's a bit more involved in terms of calculation, and I'm going to show you what we did. So the idea is that we try to find, so we're speaking about the solar cells where we were looking at the upper layer, and now the lower layer, the photoactive region, it's a solar absorber. And so we would like to be able to find good solar absorbers. And so these solar absorbers is really the region that once the photon gets in there, creates the electron hole pair. Okay? So what you want for these absorbers is that they have a good efficiency. And this efficiency is driven by the carrier lifetime. Because if the electron and the hole recombine and do not go to the gates, then you have lost what was captured by the photon. Okay? The photon. So what happens is in this material, you can have different kind of things that happen. Once you have the light that appears, you can have the two electrons that separate, okay? And this is what you want. But as I was mentioning, sometimes what happens is that they collide and then they recombine, and so you have lost everything. So you want to avoid that, okay? Okay, so this process that I just showed, the recombination, it is controlled mainly by what is called the Shockley-Reed-Hall non-radiative process. So I'm going to show you the different kind of process that can happen. And this process is a process in which the two recombine, the two carriers recombine, and they do not, so it's non-radiative, so there is no emission of photons, okay? And to work, these require some defect states. So basically, in the material, so if you have a conduction band, a valence band, so there's the three kinds of process that can happen. When you have some light that happens, you have created electron hole pairs. Okay? So a radiative process is simply the electrons going on one direction, or the photon all going in the other direction, and then emitting some photon to to remove the excess of energy. In a non-radiative process, the excess of the energy is, as I was mentioning, is released by phonons. Sorry. And so what happens, again, we have different processes that can happen. You see that you need a trap level there. And what happens is that you can have one of the carriers that goes on the trap, and then there's the other part of the, so it's a two-step process, if you want. And in the same way, they can go all the way, and so everything recombines. And in that case, everything is lost. Okay, you really want to avoid that. And the last kind of process that can lead to a recombination is that the excess of energy is given either to an electron or to a photon, basically, and as a result, this particle is accelerated. Okay? But the most important part is this non-radiated Shockley read Hall recombination. And these are driven by the position of the defect in the band gap. As you see, it's a two-step process. If one of the distance, so you see you have to do two jumps, the electron has to do two jumps. If one of the jumps is big, then it's not likely to happen. So if you have what is called a shallow defect, then it's not likely to happen. Okay. So in practice, yes. And the other point is the capture cross section, because if you have the defect, it needs to capture one of the carriers, and so this is measured by the capture cross section. Okay. So the deep defects, so the ones that are basically roughly at the same distance from the conduction band and the valence band, are the ones that are the more detrimental, because indeed you can do two equivalent jumps to recombine, and that's what you want to avoid. Okay, so as the capture cross section is very demanding in terms of calculation, we have assumed in a first model that we could take the same one for all the materials, and so we have a model that only depends on the position, so what is called the transition level of the defect in the band gap and the formation energy. And as you see in this plot, so we have taken a number of materials that are experimentally known to be bad, so to have a bad efficiency, and some are supposed to have a good efficiency. And so you see the experimental prediction, the experimental measurement, and our prediction of the efficiency, and you see that we have a good level of prediction. We have very few systems, so basically just these two here, that are predicted to be bad, that are predicted to be reasonably good when actually they are bad. In most of the cases, we are in this green region where our prediction matches the experimental conclusion. Okay? So we have set up a funnel in which the first point that we do is to test the stability. And so here we tested 8,000 compounds. Based on the stability, we looked at the band gap. And so as you can see here, from the color and of the border of the different pieces of the funnel, we use different levels of accuracy for the calculation, because some of the calculations are very demanding. Okay, so for instance, doing the band gap with HSE is something that we can afford, and so we do it. Okay, and based on that, we reduce that to 25 compounds, and for those 25 compounds, we had to do more demanding calculations, the point defects, which we did at the PDE plus HSE because there's a correction. Okay, and thanks to that, we reduced the number of candidates to 6, and for those, we did again the defect calculation, but with a more accurate functional DHSE calculation. And you see the way, so you reduce the number of compounds in such a way that the most demanding calculations are done only for a very limited number of compounds. Okay, and for those, we even did calculation of the capture coefficient, okay, the one that we had set apart, and the one of the intrinsic mobility. So these 6 materials that we selected in this approach, they can be sorted in 2 categories. We have 3 that are really defect tolerant. So that means that all the defects have levels that are either close to the valence band or close to the conduction band in such a way that you can have a small transition, but not a big one. Okay. And we have also a few systems, for which, in fact, there is a deep defect. Okay? There is many shallow defects, but there is only one deep defect, and that deep defect has a formation energy that is high. So it means that it happens not very often, it's very rare. Okay? And so the last thing we did is when we look at these materials, we can then look at them from the point of view of the global impact, because there is some elements there. And so you need to see whether the elements are earth abundant. If they are not concentrated in a country where there is some issues, if it's coming from Russia at the moment, it's not very good. Okay, so we want to see also these kind of things. And what we can look at, so there is this coefficient basically that's the HHI production. So the green region that you have there means that it's good in terms of production. It's rather easy to produce. And then we have also colored the point based on what is called the companionality. So some of the elements, when you go in the mine, you can get this element and another one, and you get basically the other one for free because you are very interested by copper, for instance, and there is something else coming with it. See, and so these that come for free are very interesting. Okay? When you look at that, in the end, this one that's at the top here, yes, this one here, and oops, sorry. And this other one here, this other one here, are two candidates for having a low HHI in terms of production. They have a high efficiency and they have a low companionality, so they basically come for free. Okay, so these are very promising materials. Please?
Materials novel materials?
Sorry?
Are these materials novel? They are not synthesis?
No. I mean, since we start from the ICSD, they have already been synthesized. It's just that people never considered them for this application. Okay? Sometimes people test something for a given application. Remember this morning when I was showing you the funnel, some of them go to the dumpster. It was not useful for a given application, but it's useful for another one. Okay? So that makes sense. The material is known, so you cannot patent everything. For this application. You cannot patent for an application. You would have to go into the details, not based on our calculation. You really need to have someone that tests it and then puts it in, and then you can test it. I mean, from the theoretical point of view, it's very difficult to patent. Okay. Okay, so now a few points about the limitation of this funnel approach, which has been used. And yesterday, Anubhav was showing you plenty of discoveries that have been obtained in this way. Here, I went into a bit more details of how you build your funnel. And building this funnel is really the crucial point. You really need to spend time in thinking, what is it that I want? How do I test that the material has this requirement? Okay, this is really important. So, a few limitations of this approach. In most of the ICTP studies, so DFT has been used at different degrees of accuracy. Well, as I was showing to you, I'll show you an example in which there was PPE and HSE. And so the computational cost of this calculation can be really a problem because if you need to have the bandgap, it requires more time to do that. Okay? So this to be solved, as we will see, by machine learning. But there's another important drawback. That is the fact that I have to feed my funnel with materials. Okay? So I need to have a list of materials that I will test. Okay? So basically that answers a bit your question in the sense that we started from ICSD, which is known. Okay? You can start doing changes in the material, but that gets even more complicated. And you're not sure that it can be synthesized. Okay? So the initial choice of the material is really important. So either they come from some given database, or as I was mentioning, you can do substitution. But most of the time, because you put some knowledge in what you put there may be some bias. So you may not find what is interesting. Okay? So, I mean, it can work. I showed you that. Anubhav showed you some examples, but there's a limitation. And this is where I was mentioning one possible approach is to make things faster by reducing the computational cost using machine learning. Okay? The problem, as was already mentioned, is that okay, you can get them through Optimate, as you have seen. But the problem, as I was mentioning, I showed you already this graph, is that most of the time, the properties that are complicated to calculate are those that you don't have very much in the database. Okay? So when you want to do machine learning, usually the more you have data, the more accurate you are. So you see the predicted power here grows as a function of the amount of data that you have. Okay? And so depending on the model that you use, so depending on the model that you use, if you use a random forest here, you can get quickly a reasonable result, but it doesn't improve when you put more data. if you go for more advanced neural network or graph networks, you will need many more data to get the result. But you can improve the accuracy. Okay? And the problem, as I said, is that the thing that you want to replace by machine learning, if you tell me I need to relax the structure, I would just tell you just do a DFT. It doesn't have that much to do with that. But if you need to compute something more involved, then you would like to do machine learning. The problem is that we don't have data for this. Okay? So we have developed Modnet, which was mentioned yesterday by Anubhav. So the idea is that we have a neural feed-forward neural network, and we try to use an optimal set of descriptors. So the idea is that we do feature selection by an algorithm that's based on relevance and redundancy. So something that is relevant is something that has a strong relation to the target. Okay? Something that is redundant, if I already selected a feature, then if I bring another one that is connected to that feature, that's not interesting. Okay? And so this thing allows us to put some prior physical knowledge, some constraint, into the model in such a way that we reduce the space that we are supposed to optimize. And so we don't need as many data as a neural network that is not being reduced in size because of this feature selection. And as a bonus, we've introduced something in which we have an architecture that allows to learn several properties at the same time. And I will give you an example. So just a few words about the approach. If you have something like that, something like this, the feature is not related to the target. So you don't care about the feature like that, okay? Because it's not giving you any information about the target. On the other hand, if you have something like this is a feature that's strongly related to the target. So you really would like to have such a feature, okay? So how do we measure the relation between the feature and the target? You may know what is called the PeerSummary Coefficient, okay? Which basically is 1 when you have a perfect correlation between the feature and the target. It gets a bit smaller than 1 when there is a bit of noise, even smaller when there is just a trend. When there is nothing, that the R is 0. And then you can have the negative ones in which you have the negative correlation. Okay? So this is an interesting way to do it. The problem is that the PeerSummary coefficient tells you that this is R equal to 0, but it also tells you that a perfect parabola has an R of 0. So it says that this is not related. This is not something that is interesting. Okay? So what we decided to use is called the normalized mutual information. And basically this is defined, so the mutual information is defined when you have two variables by the measure of the mutual dependence between them. Okay? So it quantifies how much you know about one variable when you know another one. So how much do I know about X if I know Y or the reverse? Okay. So basically, you can have this plot here where you have so these are the entropies, so the H are the entropies, and the common part is the mutual information. And basically, so if you can normalize it in such a way that it goes from 0 to 1. 0 corresponds to the case in which there is no intersection. So you see the one, this thing. So basically, you see this case here, there is no intersection, so the mutual information is 0. In contrast, when they are overlapping, when I know X, I know completely Y. This is a mutual information. Okay. So what we do is that we use that to select the feature. And so the feature helps us to see what's the underlying physics. So this morning we saw with CISO that was one way to see the underlying physics is by having a model that's analytic in terms of the feature. Here, the model is not analytic in terms of the feature, but it tells you this feature is the most important one. So for instance, here we have a plot of the entropy as a function of the first selected feature, and you see that there's a clear trend, and this first selected feature is related to the interatomic distance. So the entropy decreases when the distance between the bonds increases. Okay? And then the coloring of the point is the second feature, And the second best, most important feature is the one that gives the valence range of the constituent. And so this is some kind of measure of the ionicity of the bond. Okay? So we see the clear trend that goes from purple at the bottom to yellow here. So there are clear trends in the feature on the effect of the feature on the property. Okay, so once we have selected one feature, how do we select the other ones? So what we do is that the first selected feature is the one which has the highest mutual information with the target. And then the second one is one that has lots of mutual information with the target, but at the same time, it doesn't have much mutual information with the selected features already, in such a way that it's not redundant. The point is that each new feature needs to bring as much information as possible. That's the idea. Okay, and so you have a formula here. You can tune the parameters, and so basically you add features one after the other up to you reach some level of accuracy, or when you say you have decided that there is enough. And so we have this thing, and furthermore, we've introduced the possibility to learn several properties at the same time. So basically, these at the right-hand side here are different targets. So it can be one property, another property, or for instance, one property at different temperature, another property at different pressure, something like that. Okay, and so you try to have a part of the neural network that is common to all the properties, and then you have parts that are specific to some kind of properties, and at the end to some kind of temperatures. Okay, so thanks to that, we have Modnet. So Anubhav was showing you an old version. So this is a version that I captured on Sunday. So this is a very recent one. They told you about MatBench, where we tested the different models. And as you can see here, the model which is in orange is doing very well in many cases. It's leading in 4 of the tasks. And actually, we have an improvement. We hope to be between 7 or 8 of those. And so you see, you have this MatBench where you test the different models. You can try them. So here, we're kind of happy using MatBench. So just to give you an example of what can be done with that, one of the important points is that we are interested by the phase stability. Remember, in my funnel, the phase stability was one of the first criteria. Okay? We can evaluate the phase stability, and this answers one of the questions. This is a convex hull question. So the convex hull basically is that, in this case, it's a copper oxygen system. This is pure copper. This is pure oxygen. And what you do is you plot the energy as a function of the composition for different structures. Okay, so all the points correspond. So if you go on one line, it's a given composition, different structure. Here you see you have the same composition with different structures. And so you rank them from the highest in stability, the highest in energy to the lowest in energy. And then once you have that, you can draw lines from one to another. And everything that's above the line will not be stable. This is what is called the convex hull. Okay, that's the example of a tube. Okay, so this can be done at 0 K. So no temperature, we do DFT calculation. We can rank the structures and say, at this composition, I believe that this is the structure that's going to form. Okay, but we would like to have that in temperature as well. And so to do that, we need to include the vibrational entropy. And if you do that with DFT, which can be done, okay, it takes a huge amount of time. We computed, as I was mentioning to Omarulu, 1,500 compounds. It really, literally took millions of hours for 1,500. So what we want to do machine learning.
Excuse me?
Yes.
On the convex hull, what about those that lie in the corner?
What do you mean?
Like those on the line. Yes.
Yeah. So basically, for instance, so the way you determine it, let's say that you don't have this one. If I draw a line from here to here, then you see that this one is going to be below the line. Yes. When you are below the line, you're stable. So then you should not draw the line that I was drawing. You should draw the line to those that are stable. Okay, so basically the way you do it is that you draw lines, and if you have something that is below the line, then you need to change the lines. Okay. Okay. So just to show this work, the calculation of the phonon, so you first need to set up a workflow, and this is not an easy task. So this was done with Fireworks with a Binit. Okay. So we need to do self-consistent isolation. Then we need to compute all the perturbation with the phonons. the electric fields, then we need to merge everything, we need to analyze the data, and then we insert that in the database. And if you go on the materials project, you will be able to see the results of our calculation. Okay. So as I said, we computed 1,500 compounds. The data are available openly on scientific data and on the materials project. And on the materials project, if you go there, you can even see how the atoms move. You can click on the different points and see how the atoms move at a given Q point for a given time and so on. But so as I said, it's millions of hours just for 1,500 compounds. So yeah, I should have switched to the two slides. It should have been the other way around. So it can be done with DFT, but now let's use machine learning. Okay. So it has been done already before we started. It had already been tested to obtain the vibrational entropy at a given temperature, okay, as just as a function of the chemical composition. So that's a work from the group of Stefano Piccarolo, we will see later in this week. So that's the cross that you have here. We did a complete calculation of a random forest that was just depending on the composition, and we checked what was the effect of the training size. Okay, if you include the structure also, you can do a more advanced random forest, and you see that you improve the accuracy because the error is much smaller. Okay, then we tested both Modnet, which is our model, and Magnet, that was maybe mentioned yesterday by Anubhav, which is another model, which is a convolutional graph network, okay, which requires more data. And so when there are fewer data, our model performs better. You see that we have a lower error. And then, yeah, so this graph is to show that if we didn't do feature selection and use the simple neural network, so you again have in pink Magnet, the same as in the previous graph. It's a zoom here. The purple is our model. And then the other one is a simple neural network where you don't do feature selection. So you see that when you have little data, the feature selection is really important because it allows you to go from here to here. Okay. And then finally, our last thing is that because we have the entropy at different temperatures, we try to learn, and all the thermodynamic properties at different temperatures, we try to learn them all at the same time. And this further improves a bit the result. Not very much, but a bit. And so as a result, finally, remember you've seen from Anubhav those curves where you have the different quantities, so the entropy, the enthalpy, the specific heat, and the internal energy as a function of the energy. So the solid lines are those that are computed from DFT. The dashed lines are the ones that are machine learned. And you see that we can get very good results in most of the cases. Sometimes we have examples where it's a bit less good, and we're trying to improve that. So thanks to that, we can do now look at the stability as a function of temperature. And you see that there can be changes in the order of the structures. At low temperature, the red here is more stable than the purple, but at higher temperature, it's the contrary. So you see the importance of taking into account the temperature. Of course, you need to pay attention to the limits of your model because it's a machine learning, so it's not perfect. So there's an error bar, and so you need to take that into account in the screen. Okay, let me go now to briefly to this global optimization. How much is time? 12 minutes. Okay, I'm going to go fast then. Okay, so the idea. Okay. Okay, so what's the global optimization? So there are methods to do structure discovery. So here I'm listing a few well-known codes like AIRS, which basically what it does is that it randomly samples. So you want to, to go in this space to optimize the property. So one of the property is the stability, and so you can try to find the stable structures by going randomly on this space. Then there are other methods which are called evolutionary algorithm. There is the method USPEC and Calypso, and those allow you to move in the space and to try to find the minimum. And there's yet another one which is called the minima hopping, and these are basically the methods that are around in terms of moving in the space to try to discover things. Okay, there's a very good review here that I'm mentioning, so I'll put my slides online afterwards, so in such a way that you can access that. And then the thing that is now evolving and that is being used more and more is called Bayesian optimization. So what is Bayesian optimization? Is that we are trying to optimize a function f, which we don't know. We don't know. We know just a few points of this function, okay? So for instance, you have here 4 points. And if I give you this function, you may think, okay, it's kind of easy to get a function that passes through all the points. For instance, I can get this function here that goes through all the points. Okay, but if I've given you these 4, I've given the points to someone else, maybe you would have come up with this function that also goes through the 4 points, or this one that goes through the 4 points. So there's many functions that go to the 4 points. And so what you try to do is to get an envelope that tells you at these points here, I know that the function is here, okay? But in the middle, I don't know, it can be somewhere in between. Okay, so you have an uncertainty that you will use to try to optimize the function. So you have not only the function, but you have an uncertainty. Okay, so there are actually 2 approaches to try to determine what is the next point that you're going to compute. So it's the next attempt, and you define this next attempt through something that is called the acquisition function. So let's say that we have this function, sorry, here, and there's 2 modes actually. The first mode is called the exploitation mode. The exploitation mode is to say that the next attempt is going to be the one that optimizes the mean of the function. So this red line that I showed. Okay. So if I'm to optimize the mean, where is the maximum of this function? It's there. Okay. So my next attempt is going to be this point. But I can be completely wrong because the function can do something like the green line. Okay. And so instead of, I computed the green point, the white point, but actually its position should be here, not where I predicted it. Okay. So I can be wrong. Second approach is exploration mode. The exploration mode says that the next attempt is the one where I have the most uncertainty. So I want to know more and explore it because I don't know what's happening there. So I want to know. So I'm trying to find where is the largest uncertainty, and this largest uncertainty is here. And so I'm going to compute my next point there. Okay. Again, of course, it can be completely wrong. And so the whole thing is that in the end, you try to find an acquisition function, which is a balance between exploitation, so going where the function is optimal, and a point where you don't know a lot. And so you balance that through a parameter of data here. So you have the mean, the uncertainty. So you go where this thing is optimal. Okay. So just to give you a quick way to show what happens. So you have the function, the good function is the black one. What we know at the moment is the purple one. And so based on this acquisition function, you determine what's the next point. I'm sorry, you determine what's the next point. Determine what's the next point that is going to be tested. So the way it works is like this. See, you determine the next point, and in the end, you get something that starts to resemble the black line. Okay, so you determine one point after the other. Okay, just a few words about this generative approach and the inverse design. So basically, there's been a few papers in the last 2 years about inverse design. There's one about molecules, which is from the group of Alain Assaouzi, and then another one about crystal structure, and actually a third one that has recently appeared from the group in Darmstadt. So basically, what you use there is what is called an autoencoder or an adversarial neural network. The idea is that you try to define a space of low dimension in which you can travel there, and from there you generate models. Just to show you that this is the paper from Darmstadt that I was mentioning, just for your reference. But basically, the idea is the following. You really want to do this. I don't know if you've ever seen this. With images, you can go from a man to women in a uniform way. So if you have defined this latent space in which the images are, you can travel. There's a region that corresponds to men, a region that corresponds to women. So if you travel your point from one to another, you can generate pictures that go from the woman to the man. And what we'd like to do is to do the same things with properties of materials, going, for instance, from a wide bandgap to a small bandgap. And this hopefully can be done through inverse design and those generative adversarial network or autoencoders. And so with that, I think that I showed you that materials informatics can help discover materials with specific properties. And then I would like to thank my collaborators. So and my PhDs and postdoc in Louvain-la-Neuve, the police in Berkeley, including Alibaba, yesterday. Thank you very much for your attention, and I'll take some questions. Questions, yes?
Okay, so thank you for the presentation.
Welcome.
When we screen using the mobility, the algorithm calculates it automatically and gives us the mobility, or we have to do some post processing. This is my first question.
Yeah, maybe I can answer one question at a time, okay? So let me just show you the funnel. This one here, okay? So, okay, the screening of the mobility is done in 2 steps. The first step, you see, we look at the effective masses. Okay, so because the mobility is given by NQ mu, sorry, NQ, and then, sorry, the conductivity is given by NQ mu, and mu is related to the effective mass and to the scattering time. So you need to have low effective mass and a long scattering time to have a good conductivity, mobility. Okay, so in the first step, you just focus on the mobility, and we say that the idea is that even if you have a high mobility, a high effective mass, there are few chances that it's going to be counterbalanced by a very high scattering time. Okay, so you discard everything that is a low effective mass. Okay, then once you have a limited number of compounds, you can look at this intrinsic mobility. And so what we call intrinsic mobility is just the mobility that is governed by the electron-phonon coupling, because you have electron-phonon scattering, and that defines a tau, so scattering time related to the collision between electrons and phonons. Okay, you should add also the collisions with the defects and possibly with other electrons. Okay, so we do that in 2 steps. And so for the effective masses, there's already a database that was mentioned yesterday by Anubhav, that was created by Professor Ricci, which is an empty control. So you can get the effective masses and already do some screening based on that. For the mobility, we have recently developed a method that allows us to do the calculation in a reasonable amount of time. The alternative approach is doing one-year functions to do interpolation for the electron. So it's EPW, is already disclosed. It is electron phonon 1 year. Okay? So we have an alternative approach that is a bit faster, we think, and so we use this approach to do the calculation. So it can be done, but I mean, it's heavy calculation. So it's not like, okay, the algorithm gives it. Yeah, it gives it, but it takes time and there's some knowledge to do.
Okay, thank you very much. My second question was a carrier separation.
Yes.
You are trying by GTEC, yeah? This show
The recombination.
Yeah. Or the recombination, yes. Is it possible to use also like type 2 alignment, bandgap alignment? If you use 2 different materials, you can easily dissociate electron and hole, and they will not recombine because they are in different materials. So is it feasible to incorporate this thing in the machine learning?
I mean, it's feasible, but then it's very involved because you need to do an interface calculation to obtain the band alignment. It's not an easy to do the band alignment. Okay? So here we just look at the intrinsic mobility in at the Shockley redo combination in the absorber. We don't look at the interface. The interfaces are going to bring further problems. So you're right. I mean, one should do that as well. It's already very demanding. So it's a lot of calculation.
Thank you.
Okay? Yes.
Thank you for the response. Suppose I predicted specific transport properties for a compound. Now I want to is there a way in machine learning to apply external parameters such as electric field or magnetic field to see how this property can go through the applied fields?
And again, for machine learning, we need data. So we have data about that where you can develop models to use human limit models. The problem is that to do machine learning, you really need to have data. It's very hard. It was mentioned by Matthias, it was mentioned by Alessandro, I'm repeating it. You really need to have data, and then only you can do machine learning. It's difficult to do machine learning if you only have 2, 3 points or 10 points. It's not going to be accurate at all. It's going to be bullshit. Okay? So you really need to have information to learn. You cannot learn from nothing. Machine learning comes from data that you have, and then you learn the model. Okay? Yes.
Thank you for the presentation. I'd like you to say something about the quality of bandgap produced by DFT.
Well, I think it was already mentioned a bit yesterday. So the band gap, you see here, there's a first screening on the band gap, which is a PBE band gap. Okay, so we know that it's bad. It's underestimated. Okay, but since we know that it's underestimated, if it's, I don't know, like 2 EV, we want a band gap that is bigger than 3. If we have a band gap of 2 EV with PBE, okay, say let's keep this material. If it's a band gap that's 0.2 in PBE, there's few chances that when you have the good band gap, it's going to be 3. Okay, so we do a first screening like that. And then, as you can see here, the second step is done with HSE. So that's one in which we trust more the results of the calculation. We could do GW calculation, but we don't want to do GW for 74 compounds. Okay, so we know that it's underestimated. Okay, and then, as was pointed out by Anubhav, we start to have models. In our case, we have submitted 2 papers recently about that, about how to correct the PBE band gap to match the experimental band gap using machine learning. So this is, was mentioning the fact that you use 2 different, so you can either learn the correction between PBE and experiments, so you can do machine learning. When you have the data for both experiments and the machine and the PBE, okay, you can compute the difference. And if you have a large database enough, you can learn this difference and use that to correct. Okay, so you have a new predictor for the band gap, experimental band gap. So you have something where you need to do the PBE calculation and then correct with a machine learning. Okay, and we have another one in which we treat the fact that it's PBE as a noise. So we have a denoising procedure. So we try to use all the data that is available to denoise the data and to make a better prediction of the experiment. And then there is the approach that I mentioned of tricking long, where we use what is called multiplication. So there are ways to try to deal with that. It's not perfect, but it's better than nothing.
But I think also many of people using machine learning to develop.
That's another thing, yes. So there's people that are trying to develop a machine learned exchange correlation functionals, or even to machine learn the density to have the right density, and then there's plenty of things going on for the moment. But I mean, you will admit that doing machine learning is the fastest overall. It requires data, but once you have the data, it's very fast to make a prediction. Even if it's not super accurate, it's very helpful. The machine learning is really helpful when you want to do this kind of screening. Because at the upper layers here of the funnel, if you can reduce the number of compounds that you can do for more demanding calculation, you are very happy. So if you can screen, I mean, I could add here an extra color for the method and put machine learning. You see? And if I could do machine learning at the top to reduce the number of elements, that would be really cool. Yes.
Thank you for the presentation. Maybe based on that criteria, and especially for solar materials, have you been able to analyze plasmonic materials or solar application?
We haven't. It could be possible to analyze plasmonic. I mean, again, we need to do the calculation. You really need to think about what you put. Okay, so what is the funnel that you would put if you were to analyze plasmonic? This is where the thinking comes. Okay, just doing the calculation is not what is the most as Omolulu was pointing, it's just machines running. Okay, but the thinking is to be done in in how to set up this funnel. Because for instance, if I say from the beginning, I'm going to screen based on the intrinsic mobility, I mean, there's no way I can do it. No way. Okay. I mean, maybe here I remove some compounds that would have been interesting. Okay, but I'm ready to take that if I can get a few good ones. And you really need to put a lot of thinking, what do I first screen? Okay, can I afford to do this calculation? Okay, or maybe should I do, as you can see here, you see bandgap appears twice. Okay, the effective masses, there are only once, but the point defects appear here and they appear here. Okay, and you redo the calculation thus with less compound on a more accurate level. This is where we put all the thinking. So our brain is there. It's in this picture. Okay.
There's a question in the chat. How successful is inverse design in new material discovery?
So yeah, we can have a look at the last paper. I think I put the abstract. No, I didn't put the abstract. But I think that in this paper, they found some new compounds. So how successful? So typically we had a seminar Friday with the last author, Hong Jang, was presenting this work to us. And so basically what they did, because in this case, okay, he told us that once you generated the material, you still need to do a DFT calculation. So you don't want to generate too many because you're going to do the DFT calculation afterwards. But so there is a rate of success. You can look at the articles and they predict some new structures. It's not perfect yet, but it's in good shape, and I think the guys are improving, and we're going to see what different people can bring to that.
The inverse design is that you have a property and you try to find what the structure will be.
Yes. For the moment, what they do is that they try to find stable structure. They're not yet at the point where they say, okay, I would like to add, so we would like to go there. I want a material with a binding gap of 2.5. Yeah. What is the material? Okay? Yeah. Well, I think we can go there. I think we can. No, I'm sure.
The reverse is like give me the structure.
I can tell you that in a few years we will do it. I mean, look here. I mean, they can do this. So if you can do that, okay, there's no reason why we cannot do the same as before. Okay, you put the points, whereas then you have here the three dimensions. Low band gap, high band gap, and then still, I mean, we're still looking at, so there's two problems. One is to find what is called the latent space. So basically it's a dimensional material reduction. You see here, you start from something which is like this, and you have this space where you're going to move. Okay, and you need to find a good space. Okay, so that's one problem, finding a good space. And the other problem is you need to have something that is a representation of the structure that is reversible, because what the algorithm does is that it starts from a point here and then generates something. But once you've generated it, you need to see what's the material that corresponds to what you generate. So here they do that with voxel. So that means that what they do is that they put, you see, Gaussians where all the atoms are. So different species are, each of them is a voxel. So you reconstitute the voxels, and from the voxel you can say, okay, there's going to be one atom here, atom there. Okay, so I mean, it works. It works.
Yes, again, an instance where using different calculators, one tool is okay, different calculators do your High-Throughput. An instance where one of them fails, and one of them participated, and the other.
So what is it that you call the calculator?
Like codes, the information you use happening.
Yeah, we don't use only Abinit. We use Abinit and Fast. Sometimes, at some stages, we use also Quantum Espresso. At the moment when we didn't have the mobility in Abinit, we use Quantum Espresso and NPW to do that. Yeah. And so yes, it can happen that there's some failure, but this is where we need to spend time and try to see what's going on. And that's where the workflow, the development of the workflows is really important, because you want something that deals with as much as possible with all the possible errors. You don't want to do that by hand for even 100 of compounds. That would be too much. You can do it for 1, 2, 3, 4, 5 maybe, but don't not for 1,000.
Okay, thank you very much. So let's thank Gian-Marco.
Can you do that? That'd be great.
Gian-Marco will be around for those people that are attending this study. So now we stop. The next.
Should I stop the recording?